Hello guys, in this video I'm going to explain about the structural level of writing Verilog code for half adder. You can see I have written the code already. Let me pre-assume that you know about half adder. If not, just take a small look of how half adder actually is. For half adder, the inputs are A and B. These two are inputs, and the possible combinations are there would be four possible combinations: 0 0 0 1 1 0 1 1, and the outputs are sum and carry. So the output is sum. If you write the k-map equation for sum, this is simply, you can say, because inequality checker, so it's XOR gate, so A XOR B is the equation for sum, and for carry it's simply AB. So if this is the module of half adder, then if you are thinking to write the code in structural level, then you have to specify how the structure of this half adder is. And if you take a sneak peek of how half adder is, it's simply A XOR B is your sum, and A and B will give you the carry. So that's what we are going to write in the Verilog code. Now you just take a look here. Let me zoom this out. Okay, let me zoom in. Now this timescale directive will give you a brief idea of how many time step units you are considering. That means here it's 1 nanosecond each. So if you write hash 5 somewhere in test bench or in this, then it indicates 5 nanoseconds of delay. And this is precision, which means for rounding off the decimal values, this precision unit can be used. And now coming to the code, structural Verilog code of half adder, I gave the module name as half underscore structural. You can give any name as your wish, but it shouldn't start with numbers and all. Underscore will be neglected. Just this underscore is used in Verilog code just for users like users comfortable. If you are writing like 8 bits like this, if you are let me write 8 bits 1 1 0 1, and then if I use underscore, then I can distinguish between these, and I can distinguish between these and I can read, right? So that's why underscore will be used, and that I wrote in comment. So if you are writing a single line comment, then you can use forward slashes. If you are writing multi-line comments, then hash star will be used. Those all not required now itself. Now the outputs are sum and carry, and my inputs are A and B. And here I am specifying my inputs. Here you can see as AB and output as sum and carry. As these are continuously driven, that means whenever the inputs are changing, if A and B changes, then sum and carry will change. So no need of any memory element here. So I am not declaring any type. They are by default taken as var. So I am writing my output as sum and carry. Now directly you are writing the structure, that is XOR gate is a primitive. So the default way of writing is first you have to write the output, and any number of inputs can be there. For our time being comfortable, we are taking only two input, right? AB for half adder. So I am writing two inputs A comma B, and the output should be written first, that is sum. And similarly AND gate is also a primitive. You can give a name for this gate or you can leave like that. So carry A and B, so it's like ending these two operations. A and B will assign to carry. So if in module you can write anywhere inputs and outputs, or you can declare directly here, like you can write here itself output sum carry, and here you can write input here itself. But as we are in the beginning stage, it's better to write like this, declare separately as inputs and outputs. And now simply you wrote the code, your requirement, your structure, that is XOR gate and an AND gate's enough. Now you can check the syntax for this, which I have already done. So it is syntactically correct. Okay, now after writing the Verilog code, for simulation it's enough, but if you want to synthesize the circuit, it's always suggested to write a synthesizable code, synthesizable Verilog code. So for synthesizing, you should write the test bench also, which I have already written. Test bench is nothing but it's like you're testing with all possible input combinations. Okay, here same 1 nanosecond is taken as delay. Now if you create a new Verilog test fixture, if you add the source to the code Verilog module, then these will be given as default in itself in the software. But here you can interpret these things for inputs. For the inputs in the module, see, you're writing a separate module for test bench, that is half underscore structural underscore test. and in that you are going to write the test bench for the module. So if you recollect, the module name is half underscore structural. Now the same name will come here. Okay, now this is your unit under test or design under test, it's up to you. Now why the inputs that you wrote in the module are declared as reg and the outputs are declared as wire means the test bench, it will be like this. If this is your design under test dut, then the test bench would be like this. Okay, you are giving inputs a, b and any, if any, and you are taking outputs here. So these inputs are stimuli from the test bench. Okay, you are writing all possible combinations of inputs and you are giving them as inputs for your design under test. So that's why you should store those values, or you can also say you're using begin and you're assigning the values between begin and end in the procedural block. So that is one way of explaining why you're writing reg. And other way is you have to store these values, right? If for example in the next iteration I don't want to change the value of a but I want to change the value of b means, then a value should be stored. So that is also one more reason why we write reg here for inputs in the module, and outputs you will write wire. Okay, that is one reason which you can explain. Now if you see here, this dot notation is why, because no need to write in a particular order, they will automatically get mapped to those variables. Okay, now in the test bench you should give all possible input combinations. So here you can see a equal to 0, b equal to 0 is my first possible combination. After #2 in the sense 2 into 1 nanosecond, which is there in your timescale directive. So after 2 nanoseconds the value of a would be 0 and the value of b would be 1. Okay, and after one more after another 2, that means after total 4 nanoseconds the values again will change for change to 1 0, and after again 2 it will be changed to 1 1, and then after up to 10, here you are writing finish, right? So up to 10 the values won't change, they will remain as 1 1. So this $monitor statement is used to monitor those values and to display those values. So whenever these values that you wrote in $monitor statement, whenever they change, then you will get the output waveform printed, okay, displayed. $finish is used to complete this process and get back you to the test bench itself again. So now this is how the test bench is written. Its main intention of test bench is to synthesize the circuit and to check with all possible combinations before giving into fabrication. Okay, now let me check the syntax of this again. And let me simulate the behavioral model. Now if you look after going to the waveform again, you will be redirected back to this same window because you used the command instead of $finish, you used it as instead of $stop, you used it as $finish. So now it's generating the waveforms for the test bench. See, it's redirected back to this test bench. Now if you want to check the waveforms, you can check here. At initial the values are 0 0, up to 2 nanoseconds they are 0 0. You can see here 0 0, and the output sum and carry is also 0. If you are going for 2 nanoseconds, then it's 0 and a b value is 1. So 0 1, sum is 1 and carry. So now you can check all possible input combinations here. So after 6 nanoseconds the values will remain same. Okay, so that is what we have given in the test bench. You can modify those, you can increment those values, or you can try with possible multiple iterations and combinations. So hope you guys learned something new. In the next video I'm going to explain how to write different hierarchies there, like structural model, and then different types of abstractions are there, behavioral model, data flow. All these things we are going to see one by one in detail for as we are in the beginning for small modules. Then we are going to discuss which is more efficient for what type of coding, and what type of level of abstraction should be used for different types of circuits and all. And later we can write each thing in different types of abstraction. That's all for this video. See you in the next one.